Hello. In the last class, we have studied how to fit a straight line to a group of data that is given. Today, we will be discussing how to fit a parabola to a group of data that is given and how to fit an exponential curve to such a set of data. Let's start with parabola. Suppose we have n set of observations represented by x1, y1, x2, y2, x3, y3, etc., x and yn, as in the previous case when we discussed with fitting a straight line. X is the independent variable and y is the dependent variable. So we need to fit a parabola to this set of observations using the principle of least squares that we have already discussed. The equation of a parabola as y equal to ax square plus bx plus c, where a, b, and c are the constants to be found out using the principle of least squares. We know that for any value of x, say xi, the expected value of y is yi equal to axi square plus bxi plus c. So we will find the residuals as ei equal to yi minus axi square plus bxi plus c for any I which runs from 1 to n. For example, if say I equal to 1, then the first residual will be e1 equal to y1 minus ax1 square plus bx1 plus c. And for say I equal to 10, e10 equal to y10 minus ax10 square plus bx10 plus c. Likewise, it runs from 1 to n. We have n residuals, and after that we'll find the squares of the residuals, and then we will find the sum of the squares of the residuals, which is represented as capital E equal to yi minus axi square plus bxi plus c the whole square, summing from I equal to 1 to n. We need this capital E to be a minimum. For E to be a minimum, the necessary conditions are the partial derivatives of E with respect to the constants A, B, and C should be equal to 0. And you will test those conditions to find the constants A, B, and C. So let's start with the first condition, dou E by dou A equal to 0. When you apply this formula, we get 2 into y1 minus ax1 square minus bx1 minus c into minus x1 square, because the partial derivative affects only the term with a, ax1 square. So it becomes minus x1 square plus 2 into y2 minus ax2 square minus bx2 minus c into minus x2 square. Here also it affects only, it is operated on, in fact, it is operated on only that time with a present. Likewise, the last term is 2 into yn minus axn square minus bxn plus c minus c into minus xn square. Rearranging this, we get the above equation as minus x1 square y1 plus x2 square y2 plus etc. plus xn square yn plus, we're taking all the terms with a and taking the constant a outside, a into x1 raised to 4 plus x2 raised to 4 plus x3 raised to 4 plus etc. plus xn raised to 4. Then comes the term, all the terms with constant b included as the third term in this equation, b into x1 cube plus x2 cube plus x3 cube plus etc. plus xn cube plus the last term, which is the c term, c into x1 square plus x2 square plus x3 square plus etc. plus xn square equal to 0. So this is what we get by taking the partial derivative of the sum of the squares of the residuals with respect to A. Moving on, we can write this equation as sigma I equal to 1 to n xi raised to 4 with the constant A outside plus B into sigma I equal to 1 to n xi cube plus C into sigma I equal to 1 to n xi square equal to sigma I equal to 1 to n xi square yi, which is the first term in the previous equation. This first term goes to the right side and it becomes sigma I equal to 1 to n xi square yi. Remember this term, this equation is the end result of the operation of E with or taking the partial derivative of this E with respect to A. Likewise, we need to take partial derivative of E with respect to B and with respect to C. The second condition is dou E by dou B equal to 0, and this, as in the previous case, it yields this equation 2 into y1 minus ax1 square minus bx1 minus c, and it operates only on the term with b involved in it, so that we get minus x1 plus 2 into y2 minus ax2 square minus bx2 minus c into minus x2 plus etc. plus the last term 2 into yn minus axn square minus bxn minus c into minus xn equal to 0. Rearranging this, we get sigma equal to sigma I equal to 1 to n xi cube with a outside plus b into sigma I equal to 1 to n xi square plus c into sigma I equal to 1 to n xi equal to sigma I equal to 1 to n xi yi. This is equation 7. Likewise, we'll get another equation by taking the partial derivative of E with respect to C. And that is this equation, A into sigma I equal to 1 to n xi square plus B into sigma I equal to 1 to n xi plus nc equal to sigma I equal to 1 to n yi. So these equations, equations 6, 7, and 8 together form the normal equations. When you do these three equations, we get the constants A, B, and C, and supplying these values A, B, and C in the equation y equal to ax square plus bx plus c, we get the equation for a parabola, and we are going to fit a parabola to the set of equations. This is the technique. Let's move on to find how to fit a curve of the form y equal to ax raised to b. It's a power equation. Y equal to ax raised to b. How do we fit an equation y equal to ax raised to b, or of the type y equal to ax raised to b, to a group of data that is being given? So data from the experimental observations need not be always linear. So we need to find a method to fit equation of the type y equal to ax raised to b to that type of data. For that purpose, what we do is we take logarithm on both sides. When you take logarithm on both sides, we get log y equal to log of ax raised to b, which further reduces to log a plus b log x. For simplicity, we have taken logarithm to the base 10. We will take log y as capital Y, log a as capital A, and log x as capital X. So we can write this equation to a much simpler form, y equal to a plus bx or bx plus a. So this is linear in x and y, so that we can directly find x and y, and we know that this is the equation of a straight line. Y equal to bx plus a is the equation of a straight line. So we find these constants a and x using the terms log y and log x. Then we substitute these a and x back, so that we will be able to fit the curve of the type y equal to ax raised to b. And this is the technique. Finally, we'll have another method to fit an exponential curve to a group of data. Say y equal to a e raised to bx. This is an exponential type data. We may need to fit a curve which is of an exponential type to a given set of data. Let the set of data be x1, y1, x2, y2, x3, y3, x5, x and y as in the previous cases. As in the case of the power equation that we have just discussed, we will take logarithm on both sides. So when you take logarithm on both sides, we get it as log y equal to log a e raised to bx, or log y equal to log a plus log e raised to bx, or bx log e. Now, as the next step, we take log y as capital Y, log a as capital A, and b log e as capital B. This equation reduces to y equal to bx plus a. Again, it forms the equation of a straight line, and we will be able to find the constants a, b, and y. And substituting these things, we'll be able to fit the curve, an exponential curve, to the given set of data.